Hey everyone, and welcome back to Chem Talk. You know, where we geek out over all things chemistry.
Right, you know me.
And today,
I'm ready.
we are going deep on 6 to 6 periodic trends. Electronegativity.
So get ready to power up your chemistry knowledge because
So
this one
Electronegativity.
is all about electron battles.
It really is. I always think of it like those RPGs where some characters just like totally hoard all the best loot. Electronegativity is kind of like their stat for how strongly they pull in those electrons.
Oh, I like that analogy. So you're saying some atoms are like those total loot goblin characters? Like just grabbing all the best gear?
Totally. Some atoms are electron magnets, while some are, well, a bit more generous.
Okay, so how do we actually measure this like electron hoarding tendency? Is there like an electron greed meter or something?
Well, we have the electronegativity scale. It's basically like a ranking system for how badly an element wants to snag electrons when it's bonding with other atoms.
Oh, cool. So who's at the top of this electron popularity contest? Who is the ultimate electron hoarder? That title goes to fluorine. It's kind of like the Thanos of the periodic table, always trying to get all the infinity stones, electrons. It has the highest electronegativity on the scale.
Wow, fluorine sounds intense. So everything else is compared to fluorine's electron grabbing power.
Yeah, exactly. And here's where it gets even cooler. The periodic table, your cheat sheet for understanding atoms, it shows some pretty awesome trends in electronegativity. Like as you move from left to right across a period, electronegativity generally increases.
So why is that? Why are the elements on the right side such electron hogs?
Well, think about it this way. As you go across a period, those atoms get smaller and smaller. And the positive charge in the nucleus, it actually increases. So that just means the electrons are held more tightly and feel a stronger pull towards the nucleus.
So it's all about that nuclear attraction. Okay, so then what happens when we go down a group on the periodic table?
Things get a little less greedy, I'd say. Electronegativity decreases as you move down a group. It's almost like trying to control a party that's in a massive open world game. The farther the electrons are from the nucleus, the less control it has over them.
Yeah, that makes sense. So we've got fluorine, our electron Thanos on the one hand.
Yeah.
Who's at the opposite end? Like, who is practically giving electrons away?
Oh, that would be cesium. Way down at the bottom left corner of the periodic table. It has the lowest electronegativity and is way more likely to share.
Okay, so we've got these two extremes, fluorine clinging to electrons like they're precious loot, and then cesium generously sharing. So how does this actually affect how atoms bond with each other?
That is the million-dollar question, and that's where the real fun begins. All right, so let's talk about how this electron tug-of-war electronegativity shapes the types of bonds atoms form.
Okay, imagine you're playing a trading card game. You've got some cards that are super rare, like really powerful.
Okay, like those foil holographic cards everyone wants. Yes, exactly. No, if you're trading with someone who has cards that are like equal value, you might be willing to do a fair trade.
Right.
Yeah, for sure. A good deal where no one feels ripped off.
Right. And that's kind of like a non-polar covalent bond. Atoms with similar electronegativities share electrons pretty equally. It's just like a fair trade. They're both pulling on those electrons with about the same strength.
So it's like a balanced team where everybody is contributing equally.
Yeah, precisely.
Yeah.
But now imagine you're trading with someone who's got a bunch of like basic common cards, and you've got that super rare card. You have way more bargaining power.
Oh yeah, for sure. I'd want something good in return for my awesome card.
Exactly. So that's kind of where polar covalent bonds come in. When atoms have different electronegativities, the one with the higher electronegativity, the one that's more electron greedy, is going to pull those shared electrons a little closer. It's not like a complete takeover, but it's not perfectly equal sharing anymore.
So it's like one atom is getting a slightly better deal in the electron sharing agreement.
Yeah.
Exactly. It's kind of like trading your holographic Charizard for like a handful of common cards. You're still sharing, but one side is definitely getting the better end of the bargain.
Okay, that makes sense. So we've got non-polar covalent bonds, the fair trades. Then polar covalent bonds, where one atom is a bit more, grabby. What about those times when, like, one atom just completely dominates the trade?
You're talking about ionic bonds. This is when electronegativity differences are so huge that one atom just snatches the electron away from the other one. Remember fluorine, our electron Thanos.
Oh yeah, he does not like to share.
No, not really. When fluorine reacts with something that has a really low electronegativity, like cesium, It's a total electron takeover. Fluorine gains an electron to complete its outer shell, then it becomes negatively charged, and then cesium loses an electron and becomes positively charged.
So it's like a total electron heist. And then what happens?
Well, just like in those classic video games, opposites attract. These oppositely charged ions, they stick together, forming an ionic bond.
Okay, so electronegativity isn't just about like how strongly an atom attracts electrons. It determines like what kind of relationship, what kind of bond those atoms are going to form.
Yes, you got it. It's like the ultimate matchmaker for the elements. It dictates who partners up with whom and how they share those precious electrons.
I love it. This is making so much sense. Does electronegativity have any effect beyond just individual atoms and their bonds? Does it influence the bigger picture, like the properties of entire materials?
Ooh, that's a fantastic question. And the answer is a resounding yes. It has a massive impact on the properties of materials, everything from how they conduct electricity to how they dissolve in water.
Oh, this is getting good. Tell me more. So we talked about electronegativity and how it shapes bonds.
Yeah.
But how does this play out in the real world? Like, does it actually affect the stuff we see and use every day?
Oh, absolutely. Think of it like this. When you're building a super-powered team in a game, you wouldn't put all your heavy hitters in one place. You need like a balance of skills to make a really awesome team.
Yeah, that makes sense. Like you need a tank, a healer, some damage dealers. You gotta have a good mix.
Exactly. And it's the same with materials. Scientists, they use their knowledge of electronegativity to choose the right elements to create materials with specific properties.
Oh, so they're basically playing a real-life crafting game using electronegativity as their guide.
You got it. For example, if they want to create something super strong and durable, they might pick elements with similar electronegativities. This leads to those like balanced non-polar covalent bonds we talked about. And then that makes the material really tough, resistant to breaking.
So it's like they're choosing a team of warriors that are equally strong and work together super well. What about something like water? How does electronegativity come into play there?
Water is the perfect example. Remember how oxygen is way more electronegative than hydrogen? So that creates those polar covalent bonds, giving water a slightly positive end and a slightly negative end.
Oh yeah, it's like those magnets with a positive side and a negative side.
Exactly. And because of this like polarity thing, water is like a fantastic solvent. It can dissolve tons of different substances because those opposite charges they attract. It's almost like water is a peacemaker, bringing together all the oppositely charged particles and just like helping them get along.
So electronegativity is the reason why water is such a good dissolver.
Yeah.
Wow. What about other things, like metals? How do they work?
Metals are interesting because they have low electronegativities, meaning they're totally fine sharing their electrons. It's like they're all playing a cooperative game and everyone is sharing resources. And that's why metals are such great conductors of electricity. Those electrons, they can just zoom through the metal like a super fast highway.
So low electronegativity equals good conductivity,
Yeah.
like a superhighway for electrons.
Cool. But then on the other hand, materials with high electronegativities like ceramics, they're kind of like those single player games where the resources are super tightly controlled. Those electrons are held tightly so they don't move around very easily. So then that makes them good insulators.
So electronegativity is like shaping the whole material world around us. It's dictating how atoms bond, how materials actually behave, and even how they interact with each other.
And it doesn't even stop there. Electronegativity even affects those complex biological processes from biology class.
Wait, really? How?
Okay, so think about enzymes, those proteins that speed up reactions in your body. They've got those specific shapes and active sites where other molecules can bind.
Yeah, like a lock and key.
Right. And guess what helps make sure the right key fits into the right lock?
Don't tell me. Electronegativity.
Electronegativity. The differences in electronegativity between the atoms in the enzyme and the molecule it's interacting with, it helps create just the right attraction for the reaction to happen.
Whoa. So electronegativity is like the ultimate matchmaker, making sure the right molecules are getting together and doing their jobs. This is blowing my mind.
Yeah.
I had no idea that electronegativity was involved in so much around us.
It's truly a fundamental concept in chemistry. It unlocks so much understanding about the world and how it works at a molecular level. From like the tiniest atom to the most complex biological systems, electronegativity is everywhere.
Wow. I think it's safe to say that we've leveled up our understanding of electronegativity big time. Thanks to the Geeky Gamer Science teacher for creating this amazing episode of Chem Talk. We went from like basic definitions to real-world applications, and I think we've all seen how powerful this concept really is.
Yeah, it's been an electrifying journey.
Haha. Until next time, stay curious and keep exploring that amazing world of chemistry.